Let's talk about instruction pipeline hazard. The hazards are situations that prevent starting the next instruction in the next clock cycle. There are three types of hazard: structural, data, and control. The structural hazard occurs when a required hardware resource, does not exist, or busy, or has a conflict. The data hazard occurs when instruction need to wait for previous instruction to complete its data read or write. The control hazard occurs because the hardware does not know which instruction to fetch until it knows the conditional branch outcome. So these are the situations where the instruction pipelining is impossible. Let's begin with the first hazard, structural hazard. Again, this hazard happens because of the conflict or lack of hardware resource. A good example is memory access. If memory subsystem does not support two simultaneous accesses, the memory stage of the instruction execution and the instruction fetch stage cannot be executed at the same time, and one of these two stages would be stalled, causing a bubble in the pipeline. This is one of the reasons why we have a separate instruction and data L1 caches. Let's talk about the next hazard, the data hazard. This hazard occurs because of data dependencies between instructions. Let's use an example to understand. The first instruction add adds two registers T0 and T1 and put the results in S0. And in our simple 5-stage example, updating S0 register takes place in the last stage, write back stage. Next instruction sub needs the updated S0 in the instruction decode stage, meaning we cannot start executing the sub instruction in right next clock cycle. So this is one example of data hazard. One hardware technique to minimize this data hazard is called data forwarding, also known as data bypassing. The idea is simple. We connect the output of the execution block with the one of the two inputs of the same execution block so that the result of a previous execution stage is immediately available to next instruction. With this hardware technique, we don't wait for the results to be written in a register, but use it right away. Of course, it requires changes in hardware. Let's talk about the last hazard, the control hazard. When the hardware executes the conditional branch instruction, it does not know which instruction to fetch next until the branch outcome is finalized. Using an example of if-else statement, the hardware does not know when it should fetch the first instruction of the if body or the first instruction of else body until it knows the outcome of the branch. A technique to minimize control hazard is branch prediction. The idea is to predict the outcome of conditional branch and go ahead and fetch the instruction based on the prediction instead of waiting. If prediction is correct, there would be no stall or bubble in the pipeline. If prediction is not correct, then we throw the instruction, which could be multiple instruction, away and fetch a new and correct instruction. Hardware stalls, in this case, of course, as long as branch prediction accuracy is high, it minimizes the hardware stalls significantly. There are two branch prediction approaches. One is static and the other is dynamic. The static branch prediction is based on typical branch behavior. A good example is loop. If we think about loop, the probability of jumping back to the beginning of the loop is much higher than exiting the loop. So it's better idea to use the taken prediction. The taken prediction means jumping back to the beginning of the loop. Dynamic branch prediction is more intelligent and complex. The idea is to keep track of the recent history of branch and make a decision based on the history. It assumes that the future behavior will continue the trend. Of course, when the prediction is wrong, the hardware stalls and it has to fetch the new instruction again and update the history. Here's a quick summary of instruction pipelining technique. The instruction pipelining is a pure hardware technique that almost all modern processors implement, and it's to overlap the instruction executions after breaking down the instruction executions into uniform multiple stages. It improves the performance by increasing the instruction execution throughput, not by decreasing the individual instruction execution time. However, it is subject to hazard. There are three types of hazard: structural, data, and control hazard. The structural hazard is caused by conflict or lack of hardware resources, and solution is simply to improve the hardware or add new hardware features. The data hazard is caused by the data dependencies between instructions, and solution is data forwarding or bypassing, or the instruction scheduling by compiler. The last hazard, the control hazard, is caused by the control flow instructions, and a practical solution is branch prediction. That's the summary of instruction pipelining.